I'm Manish Kumar Mehta, currently pursuing PhD at Department of Mechanical and Industrial Engineering at Indian Institute of Technology, Roorkee. Welcome to my presentation. This video has been recorded for Internoise 2023 conference. My topic of presentation is non-destructive evaluation of FSW tool plunge depth in thin metallic sheet weld using low frequency ultrasonic lamp wave signals. So basically, I have been doing a non-destructive evaluation for weld joints by using modern NDT method uh, on the basis of based on guided waves or lamp waves. So my content of presentation is what is lamp wave, how it is used for non-destructive testing, its application, past works, what has already been done, the experiments, what I have done, the outputs and its verification, and finally conclusion and references. So if we see, there are various methods of non-destructive conventional methods are available, like dye penetrant testing, eddy current, thermography, radiographic testing, acoustic emission. These are the conventional non-destructive evaluation methods, uh, which are used, but they are sometimes costly and also they are time consuming. When suppose there is a structure here, if we want to do the inspection of this plate structure, then by using these methods, we have to inspect each and every point by placing the devices at each and every point of it. So it will take time. So to avoid it, to overcome this limitation, modern method based on lamp waves is very useful. How we can see there is a wave propagating and it is getting propagated to the entire structure. This is lamp wave. So this lamp wave will propagate to the entire structure, and we have to keep our device just at a point, and it will scan the entire structure and it will carry the information of where the defect is. And by reading that data, we can predict the failures and the defect points. So lamp waves has capacity to inspect very long range, means they can scan very big structures. Okay, and if you see the method by which these lamp waves are produced are very cheap. Like we can produce the lamp waves by just using PGT transducer, piezoelectric transducers, and they are cheap and lightweight. They are easily portable anywhere. Okay, so now coming to some more application, this modern method based on the lamp waves can be used in automotive, marine, railway, civil, chemical, mechanical, and aerospace industries, etc., etc. It is very wide range of applicability. uh, we use for inspection of bridges, pipelines. Okay, so if we wants to do inspection by conventional method, then we can do at a small point only in the pipeline. So if we wants to do long range of inspection, then at that time guided waves is very helpful. Suppose there is another example. Suppose there is an oil tank. Okay, and this oil tank is very large, means it's about 15 meter in diameters. So if we wants to do the non-destructive testing of it, then we have to clean the tank, we have to empty all the oils, and then we have to clean it properly, which is time consuming, and even it is very hazardous to human and all. So it is costly, time consuming. We can save the things, means we do not need to empty the oil if we use the modern method of non-destructive evaluation, which is based on lamp waves. We will put our devices somewhere outside and it will scan the entire structure, and our time and money and everything will be saved. So now the past works which have been done is the Taraf et al. Studied scattering behavior of guided waves in similar and dissimilar friction stir welded joints to determine elastic property of thick plates. Uh, Faki et al. Used advanced signal processing techniques to detect defects in FSW, means friction stir welded joints in thick seats. Wang et al. Has also done the same thing to study the concave cross section of the weld structures and micro structure mechanical the parameters in thick plate FSW joints. All of them has done their study in thick plates only. Nobody has done in thin plates. So this study, so there is a gap in the literature. So this study has been basically focused on the non-destructive evaluation of weld joints in thin metallic sheets, and especially thin metallic sheet weld, and weld is friction stir weld. Okay, so now in that friction stir weld, I'll be basically focus on to do the study of there are so many parameters in friction stir welding, like tool RPM and all. So if we see here, if we see here, there are two plates which are getting joined by friction stir welding, and there is a pin inside which is getting penetrated in the material and which stir the material. That's why we say friction stir. And due to that friction heat, the materials get softens and get intermixed. So this friction stir welding has a very high quality welding, because it do not melt the material up to its melting point, because in conventional welding the material get melted, and when it becomes cools, it has brittle in nature. So that's not the case in friction stir welding. So it has very good welding characteristics. Now the pin is getting inserted inside the material and it's stirred and it formed the weld. Now so that's what we wants to study, that how much pin has been inserted, because there should be optimum pin insertion for a very good weld joint. Our aim is to predict this tool plunge depth, that is how much pin, this is the view we can see here, how much pin has been inserted inside for the weld formation, by to predict the optimum plunge depth, optimum pin insertion depth to for sound welding, by not doing the destructive testing methods, by just doing non-destructive evaluation based on lamp webs. So we prepared the specimen. Material is aluminum alloy 6061. These are the dimensions: 2 mm thick plate. There are different parameters for friction stir welding. Like suppose there is a pin, which is how FSW made is the pin is inserted and it rotates to make the friction, and it move along. So there are different parameters, like what should be the traveling speed, what should be the RPM and all. So that should be the different, that are the different parameters for the friction stir welding formation. Now we try to make the different specimen having different tool plunge depths, which were very random. We don't know what is the tool plunge depth in that. So we make different specimens because our aim is to predict the tool plunge depth finally, without destructive testing. Now, in non-destructive evaluation at our lab, we have LDV setup, laser Doppler vibrometer, where we produce the lamp waves, and by sensor we acquire the data and we do the processing of the data, and we find some outputs. The input signal we used is 8 periods of 80 kilohertz Hanning window tone burst input signal, which is shown here in time domain and which is shown here in frequency domain. It's 80 kilohertz. We can see that. Okay, so now, what we have done is we have used the pitch catch method. Like suppose there is a plate here, okay, and in this plate, the lamp wave started propagating, means actuated at this point, and it propagated to the entire structure. So what we did is we actuated at some point and acquired the data at some another point by using LDV sensor. So this is pitch catch method, and what we done is there are so many modes get generated when we produce the lamp webs, like fundamental symmetric mode, fundamental anti-symmetric mode, shear horizontal modes. But we just used fundamental anti-symmetric mode, that is we say A naught mode. How we ensured that? We ensured that by calculating the velocity of the different modes, and at the particular frequency we use the dispersion curve to ensure that we have produced the A naught mode. And then we just try to calculate, we just try to measure the signal before 30 mm of the weld and after 30 mm of the weld here. sensing point 2 and sensing point 1, and we try to study the data. So we got the data. We see that we just try to got the data before the weld. This is friction stir weld top view of the specimen. So this is the signal data before the weld. This is the PZT actuator which is actuating the waves, and when this wave passing through this weld, this data is again captured at this point. So since input data is same, because we are actuating the same 80 kilohertz of frequency, but due to the different FSW welding parameters, we have just made different tool plunge depths, varying tool plunge depth, which was random, and we just we just do acquire the data for different specimens, so we get the output different for every specimens, and we just try to calculate the transmission percentage, that how much amplitude is transmitting from the how much is amplitude is transmitting from this weld zone. So we calculate transmission percentage by the formula A2 by A1 into 100. This A2 A1 is the peak amplitudes of these signals, and we found out that the amplitude, sorry, the transmission percentage is something 27%. Randomly it was 37% and 28%. So it was random, we were not able to observe something. Then what we did is we did destructive testing, and by destructive testing we just cut out the cross section of the weld, and we just this is the cross section of the weld, and we just make it stereoscopy images, means it shows the enlarged image, and this is the contour we can see, and this contour is basically the stir part by the tool. So this is the stir, and this is the bottommost part of the tool plunge depth. So this is the we measured the tool plunge depth by stereoscopic images, and it was there was different tool plunge depth measured, and what we found that again, if we come back to the slide, we found that this transmission percentage was for low tool plunge depth, this was for high tool sorry, optimum tool plunge depth, and this was for high tool plunge depth. Means we can see different tool plunge depth shows different behavior, and optimum tool plunge depth shows the maximum transmission percentage of a not mode. Okay, so this behavior can be helpful to predict the different tool plunge depth. And we also did the tensile testing of the specimen, and we observed that the optimum tool plunge depth has higher tensile strength compared to the low tool plunge depth and high tool plunge depth. It should be actually, because that's why we said optimum. It should have maximum load carrying capacity. Okay, so that's how we did the verification. We plotted the curve, and this curve is very useful, because firstly we plotted by using the destructive testing methods, because we just have to verify. But once this curve has get plotted as a standard, we can use this curve to predict for future any specimen tool plunge depths. Okay, so this paper basically coming to the conclusion, so is that we predicted the tool plunge depth by using the transmission percentage, and we found out that the optimum has always higher percentage of transmission percentage compared to the low and high tool plunge depth, which helps to predict the tool plunge depths. And now, the future scope is there are different parameters involved in the FSW, which can also be studied by using ND methods. I have done it for similar metals. We can do it for dissimilar metals also. And that's it. We have the references here. And thank you so much.